Hi and welcome. You might remember a couple videos ago I was talking about a work holding problem where I wanted to turn a taper on the lathe, and in order to do that I'd have to take my tailstock and shift it off the center axis and then turn the part between centers. However, I noted that using a pointed live center, or dead center as the case may be, is not the best solution because it only makes contact at 2 points. A much better solution would be to make a ball center. And so I was going to make adapters, and I did make an attempt to make an adapter. This isn't the live center I was trying to make an adapter for, but this live center has a 60-degree end tip angle, and that's the angle I made it for, and this fits very nicely. However, I made it for a different center. So this is the live center I was actually making the adapter for, and I screwed up because I used my machinist protractor to measure this angle here, and it is 60 degrees, and I assumed that this angle back here would be 60 degrees as well, side to side. It turns out it's not, and looking at it, I mean, I thought, wow, it looks kind of funny, but maybe it's an optical illusion. But so this guy does rock a little bit because it's only touching at one point all the way around this rear section, because this is actually about 20 degrees. But going about how I found out what this angle is might be interesting to you, so let me show you. So how did I find the angle of the center that I was interested in, that second compound angle that I can't measure directly with a machinist's protractor? And first, you need to know a couple simple rules in geometry, and don't worry, this isn't going to be a deep math class or anything. I just thought I'd point out a couple rules in geometry that may help you solve some other problems in the future. And the rules are as follows. If I have two parallel lines and a third line that intersects both lines, a couple things are true about these lines. Number one, this angle and this angle are equal. We'll call that number one. This angle and this angle are also equal. Alternate angles are equal. It also says that this angle is also equal to that by a different principle, because vertical angles are equal. So if you have two lines crossing each other, the angles on opposite sides are also equal, which would also make this angle equal to that angle, incidentally. This is a useful identity, and you'll see why. So I knew that the end of my live center, this is an exaggerated drawing of my live center, was 60 degrees, and I could measure that with my machinist square, and everything was great. I knew that half that angle was 30 degrees, and so I put my compound at 30 degrees and turned it, and everything was perfect. I assumed this angle was the same. I was incorrect. It looked like it wasn't the same, but I thought, why would anyone do that? So I didn't measure. I was foolish. So we're interested in this angle. So that angle is made by the extension of these two sides to where they intersect. And that angle here of interest is right here, right? Now in reality, we want half that angle. So I'm going to draw a line right down the center of the entire, which I missed, down the center of the entire live center tip. So I'm interested in this angle right here, which is half of the total. If you notice, if I extend this line out here, these are two parallel lines, which makes this angle and this angle equal, which means now I can measure this angle and it will be the same. So, how do I do that? I'm interested in measuring this angle right here with relationship to the horizontal, because that will give me, this angle right here will give me half of my total angle of the upper section of my live center. So how do I measure that? Well, I noticed something, that if I continue this parallel, this line out here that extends off the side of the center, and I drop a vertical from where it intersects the transition point, I have a right triangle. So if I were to take and put a measuring device to measure this change from here, height-wise, to here, and I knew this distance from here to here, I can use trigonometry to solve this problem, because this is a right triangle. And it turns out a useful relationship that tangent of that angle is equal to the rise, or the opposite, over the adjacent. The ratio of those two sizes. So, let's hop over to the lathe and I'll show you what I did. So here's the setup, and I changed my setup here. I didn't originally do it this way, but I have a DRO on my lathe, so I didn't need an indicator on my longitudinal axis, but a lot of people don't, so this will work equally well. You put an indicator on the longitudinal axis, you put an indicator on the radial axis, and what you do is, after you zero this guy, so let's just zero this guy right here, what you do is you move a known distance horizontally, like there's 100 thousandths, 2, 3, 4, 5. So I moved over ½ an inch. I'm trying to get it exact because this is a very precision measurement. And then you look at the change in height over here, and you record those two values. So now you've got your rise and your run, or your opposite and your adjacent sides of the triangle. When I did it with the DRO, I tried to measure as far as I possibly could. So I only went ½ an inch here because the way I preloaded the indicator, I could only get a ½ an inch. But the truth of the matter is that I did as much of this as I could, because the longer distance you go, the more the error is going to average out to a smaller value. So I was hoping for, rather than really tiny move, a larger move. So I did 3/4 of an inch. Let's look at those numbers. So here are the numbers that I got when I was running this test, and I did it several times. So for the height change, I got 0.2655. And for the distance, it was 0.7500. So tangent of the angle of interest is equal to 0.2655 over 0.7500. So to solve this, you take the tangent to the -1 of 0.2655 over 0.7500, and that gives you 19.49 degrees. Now, I looked at that and go, who the heck would do that? Why, I mean, unless someone was freehanding it, why wouldn't you do an even 20 degrees? So, here's the only problem with this measurement technique. It ends up being extremely sensitive to these values. I'm taking to 4 places here, which probably is not reasonable because it's pretty hard to get those values to 4 places. It's doable, but takes a lot of work. So I tried it again using the indicators rather than the DRO, just to see if that would improve my accuracy. And this distance here went from 0.265 to 0.2850, and that's actually farther off than the from ideal than the DRO based measurement. And possibly it's the way the indicator sits on the angle as well. It's got a fairly big ball tip on it, and it might not be making equal contact the whole time, because there are a little bit of damage to my live center as well. So I'm not sure exactly where the error is, because this answer should be 0.2729, and I've tried it a bunch of times and I can't get that answer. So I guess it's important to say that this can only get you close unless you are exceptionally accurate in your measurements. For whatever reason, I can't get there from here. So anyways, let's go over and make the part. So I've come over here to lathe, and I have a piece of stock loaded. It's 4130, and I started with raw stock that's 1 1/8 inch and reduced it down to 1 inch and faced and chamfered it so we could start this project. I didn't think you needed to see the dimensioning of the stock. Just one note is that this stock, this 4130, is chromoly, and the cutter leaves a terrible finish. So what I had to do is get it within a few thousandths, then file and sand to get this really beautiful finish it's got now. Anyways, interesting to note. I tried before I even did this, I wasted a whole piece of stock as I was trying a bunch of feeds and speeds, and no combination would yield me a good finish with the insert I was using, which incidentally was this Kennametal insert. And chip breaker would work, but just big bites, little bites, big feed rates, so 14 thousandths per revolution with a small bite, like say 25 thousandths depth of cut, 50 thousandths depth of cut, trying 100 thousandths depth of cut with a slightly slower feed rate, nothing would yield a good finish. Even 2 thousandths a revolution at 5 thousandths depth of cut would not create a good finish. So pretty much there was no way I was going to get a good finish out of this apparently. But you can get it to a really beautiful finish after the fact. Anyways, let's get started. First step, we're going to drill the center out to remove most of the stock so we can bore it to the proper dimension to fit this guy, my live center. So this is 0.4 something, I don't have my drawing in front of me, 0.4 something change, and so we need to drill out for that. And then we're going to match this 20-degree angle by boring. So we're going to center drill. So to find depth of my drill bit, I will first just gently let the drill bit touch my scale, and then I will hit 0 on my DRO, a project I did earlier, and then I will go back in and move in 40 thousandths, which is the thickness of the scale, and set 0. Now the point of the drill bit will be right at the face of the part that I'm working on. So now I can go in and drill the depth. So now we're going to go in 1.164 inches. This is a high helix drill bit, so I can get a pretty decent amount of depth before I have to retract it. Just like before, I'm putting a scale in front of the tool I'm using to drill. In this case, I'm using a 3/8 end mill so I can get a flat bottomed hole. And I will dial in the 40 thousandths. And I have my 0, and now I can just bore the bottom hole. Now, another way to get a flat bottom hole would be, so you can take a drill bit and you can grind the end flat and then just back relieve the cutting edges. This is a damaged drill bit I need to resharpen, but so you can cut the end flat, back relieve it, and then you have a flat bottom drill that you can get a nice flat bottom in your holes with. So next we're going to bore out to 0.470. We're currently at 0.375, and I've got this tiny solid carbide boring bar, and remind me to tell you about the company I got this from, because they're awesome for hobbyists like us, because they sell top brand surplus tooling at well, Asian prices. So it lets us get really high quality tools that we couldn't ordinarily afford. We're going to try a fairly light depth of cut just to see how this cutter will do. It is a huge amount of stick out for such a small cutter. So we're going to go for like 16 thousandths. Let's see how it does. Better than I expected. I set my 0 by taking the cutter all the way to the end and setting my 0 there, so I'm counting down to 0, which is easier. So when you're trying to measure the inside bore of a fairly small part, there are a couple ways to do it that I know of. I'm sure there are more, but the ways I'm familiar, starting with least accurate to most accurate, one would be to get your calipers in there and wiggle back and forth and look for the smallest value. The next most accurate way would be to take the equivalent of a telescoping gauge, it's a small version of split ball, and put it inside, tighten it up, wiggle, extract, measure with a pair of calipers, which are at the other end of the dial, of course. Which are measuring substantially larger value than I got on the calipers. And so 0.4059. And then the final way is to use a pin gauge, the most accurate, and that's what I'm going to do. I'm going to use this guy until I get close, and then we use a pin gauge to dial it in to get my final value. So I got a little ways to go. I've got a few passes to go, and I'll bring you back when I get close. Alright, so I've done a couple more passes off camera, and tried to bring it within 10 thousandths, and here's 0.4593. So let's go grab some pin gauges and see how well they concur with that. So this pin here is a 0.459, and it is a really snug fit. So we were actually pretty accurate, and I had to add a little lube so that didn't want it to get stuck in there. So anyways, so we got to walk in the last 10 thousandths, and I will do that with measuring with pins. So on one of my last passes here, 459, and I am going to do a 6 thousandths pass to bring it close. One thing that's important is that the closer you get, the smaller the passes you need to make, because you don't want the boring bar to deflect as it's cutting. Being carbide, it doesn't deflect very much, but it still does deflect some, so that's important to note. So I took a 6 thousandths pass, and it ended up at 66, so it's good to take small bites. I really do want to get it close. What I probably will do is, instead to get to 0.470, like the value I need, I'm going to go to 0.469 and then bring it in with some sanding paper and lap it into the final dimension. So next we're going to do the 20-degree bevel here, and in order to do that I need to set my compound to 20 degrees, and the way I did that first is I started roughly by setting the 20-degree mark on the scale on the side of it, but that's not accurate enough. So next I took some magnets and a 20-degree block, angle block, and put it on the top of my tool post, and as long as my tool is parallel to the tool post side, which it is, so then once I get this to be 0, so it's moving a tenth or two across a couple of inches, then I'm at 20 degrees. So this is a 20-degree block. I've got the compound turned to 20 degrees, which means this should be parallel to the axis of the lathe. So as I move down here, if that needle doesn't move, then I'm right on. One thing that's important to note is the center of rotation is somewhere like about where my finger is over here, and that means that in trying to set this to 0, it's like setting the nod on a mill, because your rotation point is behind where you're adjusting. So what happens is these both change in the same direction as I twist this, but one changes at a different rate than the other because it's closer to the center of rotation. So that's important to note. So the way I did it was I always approach 0 from the same side, and what I do is I'd set 0 over here, go to the extreme other side, come part way to 0, then go back. Now this one was off 0, so I'd reset this to 0 and then keep doing this. Each time it would get closer and closer until it was right on. So now we're set 20 degrees. We can cut the 20-degree bevel to match the live center 20-degree point. So now we're ready to do some passes at 20 degrees, and I have locked the longitudinal lock on the lathe so that the only thing adjustable will be my cross slide in and out for finding 0 and choosing how big a bite I want to take, and the compound to take the bite itself. So let's set speed. This is probably good, 440 RPM, and we're good to go. All right, so let's take a really light pass. Each time I set my x-axis to 0 so I can pull out without scratching if I want to do that. So here's about a 25 thousandths pass. Material finishes terribly. I'm going to try a spring pass and see if there was much deflection in the cutter taking 25 thousandths depth of cut. Apparently there was a little bit. So what I'm going to do is I'm going to keep taking spring passes until I get no material removed. So I got the opening within about a thousandth, and then I took the rest off with sandpaper. So you can see there is no play at all. That is a perfect fit. So now we just need to profile the outside and part it off, and we are good to go for the final part where we braze on the ball bearing. Now I'm just going to put some decorative banding and a little profiling for appearance. Then I'm going to part this guy off. I'm going to flip it around, and then I'm going to relieve it so that the ball bearing can get to the part and still let tools get around it. You'll see when I get there. Besides looking nice, that'll give you something to grip to pull it off of the live center, because it's going to be kind of tight. So I wanted to give some grippy bits to hold on to. So I did partial profiling, and then I'm going to flip it over and do the 30-degree end point. But remember I talked about order of operations? Again, I screwed up. I put these little grooves in here, the decorative grooves, and forgot that I have to flip this part around to hold it. And now I'm going to hold on the decorative grooves. Now, this particular collet, let me pull wide here, is a Jacobs collet, and it does a pretty good job of distributing the force, but still, it would have been smarter if I had held it first and then done the profile after, and then put the grooves in at the very end by grabbing on this part here, because this didn't take a lot of force at all. Anyways, live and learn, and I'm going to part this guy off now, and then we're going to flip it around and finish it. So next up, we're going to just put a profile on this for relief and appearance. So we're just going to work it back until it looks like we've got enough space and still have room for the ball bearing point. Because the whole goal is to get this extra material out of the way of the ball bearing that will be mounted dead center there. That way tools can get in closer. So that's where we're headed. I think we're good. I think I'm going to do a couple spring passes, see if I can clean this up, which I'm pretty sure I can't because this stuff sucks. The last step's going to be to take this ball end mill and put a little detent in the end of this that will be the same radius as the ball bearing I'm going to use. And the advantage of that is increasing the surface area, contact surface area of the ball bearing. Hopefully make it stronger. So we're going to take this really slowly. An awful lot of stick out there. So here's what the ball bearing will look like, and hopefully we'll silver solder it in place and it'll be strong enough. So now we're trying to get the balls brazed on or silver soldered onto the top of these fixtures. It's more challenging than I expected. I gotta tell you, that's incredibly hard. I had no idea it was going to be this hard. Okay, so here's the final product. I figured if I was making one, I should make several, which is why this project took me a lot longer than I was expecting. It was a big learning process. The brazing process, never done silver soldering before, or silver brazing, whatever it actually ends up being, and it was very challenging. So the first one I did was this one, and it turned out so badly I had to actually return this on the lathe. Then I went to this piece of 5/16 stock, And I got this one to work, and the trick seemed to be dip the end in flux, cut off a couple pieces of silver solder, bury them in the flux in the end, dip the ball bearing in flux, and then heat the base until it was glowing red and the silver solder was completely melted, and then bring the ball bearing slowly into the flame so it heated up, if you can hold on to the ball bearing and not have it shoot out, which it did pretty much every time. And then once you touch the pool of silver solder, it'll stick, and then you just continue heating and it'll settle in, especially since I created the 1/4 inch concave hole for it to fall into. So these two guys are for 30 degree. This one goes in a chuck all by itself, and this guy goes on a 30 degree chuck and mates. It was my first one. It was a mistake where I thought this angle here was 30 degrees like the tip, not 20 degrees like it actually is. So I made this one, but it'll work perfectly for the 30 degree live center or 60 total angle. These two are for this guy. That one's not bad. This one's an absolute perfect fit. I was very careful the second time, so you can hear it suction off. So it worked out, so now I can turn between centers, and it was a very big learning experience because of the silver soldering and trying to figure out this angle. So hope it was useful for you. Thanks for watching. Hope to see you next time.